Hello and welcome back to the Science of Concrete Materials class. This is lecture number 26 of the class, and we will continue our discussion on the aggregates. As mentioned before in lecture number 24, I mentioned I'm going to elaborate on a couple of topics regarding the calculations of some of the aggregate parameters basically used for mixed design calculations, which are the determination of the specific gravity, the moisture content, and the unit weight. And also I mentioned, we will talk about the determination of the moisture content, absorption, effective absorption, all based on the oven dry moisture state as a reference. So basically some more computations that we will need, and they will be helpful when doing the mix proportioning, because we may come across certain situations that requires these calculations. Okay, so as we said, the density of the aggregates is required in mix proportioning to establish the volume, the weight-volume relationships. So the density is expressed as the specific gravity, which is a dimensionless ratio relating the density of the aggregate to that of water. So if we recall the equation we had during the lecture number 24, we said, the specific gravity basically equals to the density of solid over the density of water. Okay, so that's, we remember we gave this a number. It was equation number 9, so just we continue the number in sequence. We started in the lecture so that we keep track of these equations. That was equation number 9. So as we said also, since densities are determined by displacement in water, specific gravities are naturally and easily calculated and can be used with any system of units. Now, it must be remembered that aggregates contain some porosity, and that the specific gravity value depends on whether the pores are included in the measurement or not. So it is also necessary to distinguish between pores that connect to the surface of the aggregate particles, which are the permeable pores, and the pores that are sealed within the particles, which are the impermeable pores. Okay, so for the purpose of this discussion, the impermeable pores will be considered as part of the solid, so we will not consider them. Okay. All right, so based on that, we can distinguish between different specific gravities, between the apparent specific gravity, which refers only to the solid material, excluding the permeable pores. We can write it as follows. Let's say apparent specific gravity, okay, equals to the weight of the aggregate. The weight of aggregate, this is solid only. You need to remember these these equations. Okay, over the volume of aggregate, again solid only. Okay, this is multiplied by 1 okay, let me, over the density of water. Okay, let's call this equation number 10. And also the other quantity, which is the bulk specific gravity, which includes the volume of the pores in the aggregate volume. Okay, and it's written as follows. We have the bulk specific gravity which equals to the weight of the aggregate which is solid plus pores, okay, over volume of aggregate, which is solid plus pores. Okay, again multiplied by 1 over the density of water. Let's call this equation number 11. All right, let me just write this better. All right. So the bulk specific gravity value is basically the realistic one to use, since the effective volume that the aggregate occupy in concrete includes the pores. You need to remember that, okay? This is the more realistic one. All right. Okay, so as we can see from equation number 11, that the contribution of the pores to the bulk specific gravity depends on the contribution of the pore medium to the weight of the aggregate. So if the pores are filled with water, basically there is a finite contribution to the weight that is absent when the pores are empty. All right, so that's something you have to be aware of and remember. If we go back to equation 11 here, it can be rewritten, as follows. With the denominator can be rewritten differently, which is basically the water displaced. So let's say the bulk specific gravity equals the weight of aggregate, which is again solid plus pores, divided by the weight of water displaced. Okay, so let's give this equation. This is a variation of the above equation, so let's call this equation 11b, and let's call this equation 11a. All right. So let us refer, to these equations as A and B, as I said, because they are the same equation, just we rewritten them based on this definition I just introduced. So based on the definition of the different bulk specific gravities we just mentioned, we can, I'm gonna reintroduce that equation number 12 we mentioned in the class. So we have the apparent specific gravity, and we have the bulk specific gravity, and we have the bulk specific gravity. This is based on OD, which is the oven dry weight. This is the apparent specific gravity, and here we have the bulk specific gravity on the saturated surface dry condition. Okay, so the apparent specific gravity will be larger than the bulk specific gravity in the SSD condition, which is larger than the bulk specific gravity in the OD condition, oven dry. So let's call this equation number 12. Okay? So since the porosity of most rocks really used in the concrete as aggregates is only on the order of 1 to 2%, so the values of the specific gravities are approximately the same. I'm saying approximately. Depend, again, based on the assumption that, the rock of a certain normal weight aggregate rocks and their, porosity on the order of 1 to 2%. But again, this will not be true for the lightweight aggregates, whose bulk specific gravities are strongly dependent on the moisture condition. Okay, remember that. The bulk specific gravity, though, let me go back to that equation. The bulk specific gravity, as I mentioned, of most rocks in the range of, 2.5 to 2.8, if you remember, we mentioned that. Okay, so a value well below this range is probably indicative of high porosity. So remember that. But, the bulk specific gravity of an aggregate cannot be directly related to its performance in the concrete. Now we're saying this is the normal range for most rocks used as aggregates in concrete. A value below that means, the aggregates contain high porosity. But again, this is not directly related to the performance in concrete. So it is not a specified quantity. I mean, the only reason for specifying bulk specific gravity is only if a minimum density of concrete is required, since the bulk specific gravity relates to the concrete density. All right, you just need to remember that. So let us see how we determine the bulk specific gravity. Okay. The bulk specific gravity on the based on the saturated surface dry condition of the aggregates is determined by the displacement method, which is given in ASTM C127 and C128. The basic equation used is equation number 11b right here. So in ASTM C127, the coarse aggregate, basically this is, for coarse. So the coarse aggregate is weighed in air, where we have the weight of aggregate in air, and again in water. Okay, and the weight of water displaced, basically again weight of water displaced, which is given by the following equation here. So the weight of water displaced equals the weight in air minus the weight in water. Let's call this equation number, 12 here, 13. So the weight of water displaced is, of course, numerically equal to the volume. This will be equal to the volume of water, because the density in the SI system of units is equals to 1. Okay, so the and also, you know, this is the same as the volume of aggregate. Okay. In ASTM 128, it's different story. C128. We have use a pycnometer, which is, you know, it's weighed full of water, a pycnometer. And then the pycnometer containing the sample of the SSD sand, fine aggregate, is filled with water and weighed again. So the relevant equation for this, you know, can be written as follows in this case, which is we have the water, weight of water displaced equal the weight of sand plus weight of the pycnometer. Remember this, the weight of pycnometer here, minus the weight of the pycnometer. Let's distinguish this from the other value with the star. Okay, let's call this equation 14, and let's see. So the weight of sand is the weight of the SSD sand here, SSD sand. And the weight of the pycnometer, this value, is the weight of the pycnometer containing only water. And this value, the W star sub pycnometer, or the weight of the pycnometer star, let's call it, this is the weight of the pycnometer containing both sand and water. Sand plus water. This one, okay? So the above equation can be reduced to the following equation. Okay, so this, it will be the water displaced equals the weight of water. Okay, something wrong with my pen. Okay. Minus, let's distinguish this value here with the star. So the weight of water, this value, will be the weight of water in the pycnometer in the absence of sand. No sand here. And the W star water, this value, is the weight of water in the pycnometer in the presence of sand. Okay? This is with sand. All right? Okay, so let's call this equation, because this is a variation of the other equation, so this will be 14. Let's call it 14b, and let's give this equation the designation A. All right? Okay. All right, let's keep going. So the displacement method, this displacement method cannot be used successfully using the oven dry aggregate, because the absorption will take place during the measurement. Okay, since the bulk specific gravity will be different in the oven dry case, we write the bulk specific gravity always with any designation where we carry the calculation. So we write it as this SSD, meaning it's done in the saturated surface dry condition. So remember this, because again, you have to refer to the condition of the aggregate where you do the determination. But this method, of course, not this method, not for oven dry case. So when we do it this way, we write it with the designation SSD to make sure we are accurate, and this refers to the SSD condition determination. All right. The bulk specific gravity on the oven dry, based on the oven dry moisture state, can be used or can be calculated using equation. Let's go back here, equation 11b actually, equation 11b here, by substituting the oven dry aggregate weight in the numerator. Go back. Let me go back here. So basically, if we substitute in the numerator, basically the oven dry aggregate right here. So this equation can be used, right? Okay, to calculate now the apparent specific gravity, basically using equation 10 above, the weight of the aggregate is again the oven dry weight and the weight of the water displaced, solid only, is the weight of the water displaced by the SSD aggregate. So minus the weight of the water in the pores. So the denominator of the equation becomes as follows. For basically apparent specific gravity, equation 10 above. Okay, so the denominator of the equation becomes as follows, which is basically the weight of the aggregate in SSD condition minus the weight oven dry condition. Okay. So remember what we said, about the about that ASG, apparent specific gravity, is larger than the bulk specific gravity based on the SSD condition. All right. Okay. So let's talk about now the measurement of the moisture content. The measurement of the moisture contents of aggregates, can really conveniently be made using the displacement methods used for the determination of the bulk specific gravity of the saturated surface dry conditions. So basically, using bulk specific gravity methods. All right, so the procedure, for determining the surface moisture in fine aggregate, for fine aggregate, this is given in ASTM C70. All right, but the principle behind this method, can be used to determine the effective absorption or surface moisture of both fine and coarse aggregates. So, for a given aggregate sample from a stockpile aggregate, we can write this relationship. We have the weight, let's denote it by the subscript stock, meaning stockpile, equals the weight in the SSD condition plus the weight of the moisture content. Okay, let's give this equation here, what number we reached here, 14. Okay, so let's give this equation number 15. So this value here, it could be either positive, meaning it's wet, or negative, meaning it's, air dry condition. So the usual measurements are then, made as if the bulk specific gravity of the aggregate was to be determined. So it is assumed that the aggregate reaches the SSD condition during measurement. So for coarse aggregate, use an equation 11b right here. Let me keep going back and forth, just bear with me. Equation 11b, we get the weight of the, based on weight of the SSD condition, and then the bulk specific gravity will be equal. Let's rewrite this equation again. So remember, we are rewriting equation number 11. Let me go back. So the bulk specific gravity, again, SSD equals the weight in the SSD condition divided by the water displaced. Okay, so in the experiment measuring the bulk specific gravity on the SSD condition, the complete weight was basically the SSD weight. But in this case, that is not true, as equation 15 here shows. But the water displaced can be expressed in terms of the weight based on the SSD condition, as shown above. So let's rewrite this equation. Let's give this equation a number though. Let's give this equation a number. Let's call it number 16. I'm going to have a variant of this equation, so let's give it designation A. And let me slide this down until I need it. Okay, so let's rewrite this equation, the bulk specific gravity here. The bulk specific gravity, again in the SSD condition, will be equal to the weight based on the SSD condition divided by the weight on the SSD condition minus the value, let's give it designation star here, SSD. Okay, let's call this equation 16b. So this value here will be equal the weight of the SSD aggregate in water. This is weight of SSD aggregate in water. All right. So this quantity is actually measured experimentally, since the aggregate attains the SSD condition before the measurement is complete. So this is always true, for wet aggregate, but could be an error or incorrect if the aggregate is very dry and absorption is slow, which is not the usual situation, by the way. So it's not the case. So equation 16b can be rearranged to obtain the WSSD in terms of, two known quantities, which is the bulk specific gravity SSD and the weight of SSD aggregate in water. So let's rewrite it. So we will have, the weight SSD equals to, that will be this value here, the weight of SSD aggregate in water, times the bulk specific gravity, again SSD, divided by the bulk specific gravity, again SSD, minus 1. All right, so let's call this equation number 17. So this value, how this value can be determined, okay? Okay, let me slide this again down until I... Okay, so let's go back. Let's call this equation 17A, because we are going to have a variant of it. So this equation 17A can, we can use it to solve for the weight of the moisture content in equation 15. Where is equation 15? Right here. Okay, so we could express, the weight of the moisture as a percentage of the SSD weight, like meaning as a surface moisture and effective absorption. So in the case of fine aggregate, equation 14A can, be adapted to solve for the water displaced, since the weight of the sand is now the weight of the sand in the stockpile condition. And, it can no longer be used in the equation. And we must write it as follows. So basically, listen to this equation here. Weight of the water displaced equals the weight of the SSD condition minus, or plus rather, sorry, the weight of the pycnometer minus the weight of the pycnometer and sand we identified earlier. So this is the this value basically measured experimentally, which is, the as defined above, is the weight of the pycnometer contained in both sands and water, as we defined it above. And this value here is the weight of the pycnometer containing only water. And again, is known from the experiment used to measure the bulk specific gravity SSD. So the weight WSSD is not known, but again, by substituting in equation number 17, let's call this 17B. So by substituting equation 17B into equation 16A above and rearranging, we get the following relationship. We have WSSD equals to following: the weight of the pycnometer star, this value, okay, minus the weight pycnometer here, times the bulk specific gravity, divided by the bulk specific gravity SSD condition here, minus 1. Of course, this one SSD also. All right. So that's how we determine the weight in the SSD condition. And let's give this designation number 18 just to keep track of the equation. Okay. So this is about the moisture content. The next topic I'm going to talk about here is the unit weight. Okay. So as we said in the previous lecture, the unit weight, abbreviated as can be defined as the weight of a given volume of graded aggregates. So it is a density measurement, and it is also known as the bulk density. But this, alternative term is similar to the bulk specific gravity, which is quite different quantity, and maybe it's not a good choice. All right, so you remember that. So the unit weight effectively measures the volume that graded aggregates will occupy in concrete, and includes both solid aggregates, particles, and the voids between them. So the unit weight is simply measured by filling a container of known volume and weighing it, according to ASTM C29. So basically, it's a known volume, and just weigh the container. So evidently, or clearly, the degree of compaction within the compaction of the aggregate within the container will change the amount of void space and subsequently the value of the unit weight. So this is a variable. So basically, the ASTM standard method, calls for compaction, by rodding. I forgot to write his 29. Compaction by rodding, just to bring some uniformity and repeatability to the experiment. Okay, so the unit weight of light aggregate is often, determined in a loosely packed condition without compaction. This is just for your information. But, for the coarse aggregate, since the weight of the aggregate is dependent on the moisture content of the aggregate, a constant moisture content is required. And again, we said, constant moisture content. So oven dry aggregate is used in ASTM 29. This is oven dry. So the unit weight of the coarse aggregate is required, for the volume mixed method proportion. So we need this unit weight required, for the volume method mix proportion. All right. So that's why basically we need it. So you need to know this unit weight if we're doing, the mixed proportion and by volume. And again, we're just introducing these values to become more familiar with these terms and the equations. Basically, these are prescribed equation in the ASTM standards. The reason we are mentioning them here, just to become familiar with them and have some background of how these values were determined and what do they mean. All right. All right, so the void space that must be filled with the mortar can be calculated. And again, we're talking about calculating the unit weight. We need to know the void space between the aggregates, which will be filled basically with mortar. Okay, so the unit weight in kilogram per cubic meter, which is the unit, basically is equal to the weight of the aggregate. We have this term, weight of aggregate, in 1 cubic meter volume. So if we look, we have the total volume equals to V sub A plus V sub V, which equals 1 cubic meter. All right. Now, let me keep sliding this down here. Sorry, guys. And if we rearrange the equation, will be equal 1 minus the V sub A. And again, this is in cubic meter. Okay, so basically this is the volume of the aggregate, and this is the volume of voids, and the void space. And again, based on the preceding equations, we can, the volume of the aggregate. Okay, I lost the track of the number, and let me go back. This is number 19 here. This equation number 19. This is equation number 20. Keep track. So the volume of the aggregate will be equal to, based on what we have presented above, the weight of the aggregate, okay, divided by the bulk specific gravity times density of water. This is just the general definition, and this is in cubic meter. And let's call this equation number 21. So this is density of water, and this is the bulk specific gravity in the dry state. So let's rearrange this equation number 21. Let's rearrange it somehow so that we have the volume of voids equals 1 minus the weight of aggregate divided by the bulk specific gravity times, of course, density of water. And again, in cubic meter. Let's call this equation number 22. And I need to slide this down again. All right. I lost the whole thing. I'll bring it back. Okay, I'm going to leave this here aside, and I'll bring it when I need it. Okay, so this is equation number 22, as we said here, which is the volume of voids. Okay, equation number 22. Or actually, it can be rewritten indifferently. We can say the volume of voids equals to, no, I'm going to have to do some rearrangement here. 1 minus basically the unit weight, remember the definition of the unit weight, divided by the bulk specific gravity, of course multiplied by the density of water, again cubic meter, and this will be equation number 23. Or we can actually express it, as percent, percent voids. Which will be equals to the bulk specific gravity, of course, times the density of water, minus the unit weight, divided by the bulk specific gravity times the density of water, of course expressed as percent, as we said. All right, and that will be equation number, we have, okay, this will be number 24. All right, okay, so as we mentioned before, guys, the unit weights of both fine and coarse aggregates, normal weight aggregates, fallen within the ASTM grading limits range. As we said, the unit weight, normal weight, based on ASTM limits. These, as we mentioned before, about the range 1450 to 1750 kilograms per cubic meter. That's the density, the range of the densities of the aggregates we use. Okay, but a plot of unit weights for various aggregate blends of two particular aggregates shows a maximum unit. Let me bring this one here now. Let me just enlarge it a bit without rotating it. So that's what I was saying. The range of the normal weight aggregates, fall in this range right here. But what I was saying before I get distracted by slide in this graph, if we have a plot, of unit weights of blend of aggregates, it shows a maximum unit weight when they find aggregates in the range of 35 to 40%, somewhere here. Okay, so let's say about 40% 5 aggregate, as we mentioned in the class, of the total aggregate, give us the maximum. Here's the unit weight. See, but it seems like it's a range about 35 to 40, but let's say it's about 40% of the mix is fine aggregate. It gives us the maximum unit weight. So if we go back to equation 22, where did it go? Equation 22 right here. It can be, deduced that the maximum corresponds to a minimum percentage of void space that must be filled with paste. Assuming, of course, the bulk specific gravities for both aggregates is the same, which is basically a good approximation though for fine and coarse aggregate, okay? So the most economical concrete is the one, this is most economical, no, I misspelled it. One that contains close to, 40% fine aggregate of total aggregate. Okay? So that's something you need to keep in mind. Basically, this one will require least amount of paste, which is basically cement. Okay, so this is from economical point of view, all right? So that's really the point, what we just wanted to go through this equation to identify the unit weight definition and figure out from that, what blends gives us the maximum unit weight with the least amount of voids. All right. So let's slide this back here up. There is, as I mentioned in the introduction, there is another topic that I really would like to cover. If you remember, we talked about, determination of, moisture content based on the oven dry moisture state. Expressing quantities in an oven dry basis, like the absorption, the absorption, effective absorption, and surface moisture. You remember these? We talked about them when we throughout the lecture, the lecture number 24, I believe it was. But everything I said, the reference was the SSD for convenience and ease to handle the equations. But also we can do this based on the oven dry condition. This is just like a parallel methodology if you need to. So let's, for example, the absorption can be written as follows. Basically, the weight based on the SSD condition minus the weight based on the OD condition divided by the weight on the based on the AD condition. Of course, times, expressed as a percent. Let's call this equation A1 because it's like an annexure to the lecture. So, and also we have the effective absorption, which is expressed as follows. This is the weight SSD minus the weight in the air dry condition divided by the weight in the oven dry condition times, again expressed as a percent. Let's call this equation A2. All right. The surface moisture can be written as follows, which is the weight in the wet condition minus the weight in the SSD condition divided by the weight and the oven dry condition, again expressed as percent. Let's call this equation A3. All right. So again, equations A2 and A3 are basically the same as the definition, for based on the SSD moisture state, except that the denominator is now the OD weight. All right. If you go back to lecture 24 to recall these equations. Okay, so now if the difference between the SSD and the OD, is too small, like 1 to 2%, as it is the case in most aggregates though, the actual differences between effective absorption or the surface moisture calculated from the SSD and the OD states can be neglected. Just keep that in mind. So when working with on the OD basis, oven dry basis, the quantity of total moisture is generally used. There's, as we can write it in this condition, total moisture equals, which is the weight and stockpile, remember that, minus the weight oven dry condition divided by the weight oven dry condition, again expressed as percentage, and again this is number 4, A4. So it can be shown that the effective moisture equals to the absorption minus the total moisture. This one, equation number 5. All right. So when the TM, the total moisture, is measured on an air dry aggregate, it becomes surface moisture equals the total moisture minus the absorption, and that will be equation number 6, A6. Or actually, when the total moisture is measured on wet aggregate, or expressing this, in general term, the moisture content of the stockpile aggregate is given as follows. This is the moisture content in general for stockpiled, or the total moisture for a wet aggregate. This expression will be used, which is the total moisture minus the absorption, and that will be equation A7. Okay, so when the moisture content again is positive, this means surface moisture. When MC, the moisture, the moisture content is negative, it means effective absorption. Okay, so basically these values, whether the moisture content, as we mentioned in the previous lecture, we need these values. We need to be familiar with these calculations, how to manipulate and handle these figures and numbers in order to, when we do the mix design, to be able whether to deduct water from the water cement ratio we specify for the mix based on the aggregate moisture state, or add water dependent on the aggregate moisture state again. So basically this is very important to be familiar with. Go through these equations, become familiar with them, and you have, like I said, to be able to manipulate and handle these equations and these terms for that purpose. And again, this is the presentation based on OD, state of moisture. The one we presented before, which is I think the more common, is based on the saturated surface dry. Okay, so this is basically the end of lecture 26 here. And next time, I think by this lecture, by this topic, with this lecture, we have finished the aggregate module. Basically, end of aggregate module of the class. So next time we're going to start on the next module of the class. So thank you for watching, and I will see you next time. Thanks again.